Welcome to the deep dive. Just take a second and think about your day, those recommendations you get online, how your phone just gets what you're saying, or even like how your map app navigates traffic. Chances are artificial intelligence is humming away in the background, shaping so much of our world, often, well, pretty invisibly. So today, we're really going to dive deep into Erik Herman's work, AI Revealed, Theory, Applications, Ethics. It's pretty comprehensive. Our mission really is to give you that shortcut, a clear picture of what AI actually is, its real impact, and crucially, the ethical stuff that's shaping its future right now. You might have a few aha moments.
Exactly. And it's more than just buzzwords now, isn't it? If you're curious about the tech that's, well, really driving things today, this deep dive is kind of essential. We're going to unpack all the complex bits, the challenges, the debates, basically turn AI from this fuzzy idea into something you really truly get.
Okay, let's start right at the beginning then. If you ask different people what artificial intelligence is, you get all sorts of answers. How do we pin it down?
Right. Well, fundamentally, AI is the science, the field, focused on building machines that can do tasks normally needing human intelligence. Think about decision-making, understanding language, seeing things visually, recognizing speech, solving problems, that kind of stuff. And the really cool part is these systems learn from data. They improve over time without someone manually reprogramming them for every little thing. They simulate or sometimes even go beyond human thinking for specific jobs.
So machines thinking, learning, but maybe not in that broad sci-fi robot way we imagine, which brings us to the different flavors of AI. We hear narrow AI, strong AI. What's the deal there?
Yeah, that's a really important distinction to make because it helps understand where we actually are versus where we might go. We usually break AI down into three types. First, there's narrow AI, sometimes called weak AI. These are systems built for one specific task. They can be brilliant at it, but that's all they do.
Ah, okay. Like the examples you mentioned earlier.
Yes, exactly. Your Cirrus and Alexis, the thing suggesting movies on Netflix or products on Amazon, even the AI helping self-driving cars stay centered in a lane. These are all super sophisticated narrow AI. They crush their specific task, but, your Alexa isn't suddenly going to start writing a novel.
Right. Got it. So what's next?
Next up is general AI, or strong AI. Now, this is still mostly in the realm of theory. It's the big goal for a lot of researchers. The idea here is to create AI with human-like cognitive abilities across the board: reasoning, problem-solving, abstract thought, and critically, the ability to learn new things, different things, on its own, like us.
Something that could learn pretty much anything a person could.
That's the dream, yeah. And then, taking it even further, you have the hypothetical artificial superintelligence. This would be AI that doesn't just match human intelligence, but surpasses it in everything: creativity, wisdom, maybe even emotional understanding.
Yeah.
And, well, as you can imagine, that idea brings up some massive ethical, even existential questions. But yeah, most AI today, definitely narrow AI.
That distinction really helps ground things, doesn't it? It separates the reality now from, like, the movie plots. So what actually makes these narrow AI systems tick? What are the building blocks?
Good question. There are several key bits working together. Machine learning, or ML, is probably the main engine room. It's all about algorithms learning from data to make predictions or decisions. They spot patterns themselves, rather than being programmed step by step for every possibility.
Okay, so ML is the learning part. What else?
Then you've got neural networks. These are kind of inspired by how our own brains are wired, with layers of interconnected nodes or neurons. They're incredibly good at finding complex patterns in huge data sets. They've really changed the game for things like recognizing images and understanding speech.
Like digital brains, sort of.
In a very simplified way, yeah. Then robotics comes in when you combine AI with physical machines. This lets robots perform tasks autonomously. Think super precise surgical robots like the Da Vinci system, or autonomous drones, or even those robots zipping around in giant warehouses.
Right, AI giving the robot its smarts.
Exactly. And finally, there are expert systems. These are older but still relevant. They're designed to mimic a human expert's decision-making in a specific area. They use a knowledge base and a set of rules to reach conclusions, used in things like medical diagnosis aids, financial forecasting tools, or those customer support chatbots that try to solve your problem.
It's easy to think AI just appeared, but you mentioned it has deeper roots. What was that turning point from just ideas to something testable?
Oh, absolutely. People have wondered about artificial minds for ages, back to Aristotle, Descartes, thinking about logic. But the big shift towards something practical, something you could actually test, that really came in 1950 with Alan Turing.
The Turing test.
That's the one. His paper, Computing Machinery and Intelligence, asked, can machines think? And he proposed the test. A human judge talks to both a machine and another human through text only, right? If the judge can't reliably tell which is which, the machine is considered to demonstrate intelligence. It was groundbreaking because it gave the field a concrete goal, a benchmark.
And from there, we've seen some amazing steps. I mean, I remember reading about Eliza back in '66, that early chatbot mimicking a therapist. Kind of primitive, but it fooled some people.
Yeah, it was surprisingly effective for its time.
But then things really accelerated. For me, Deep Blue beating Kasparov at chess in '97 was huge news.
Massive milestone. Showed AI could master complex strategy.
Then IBM's Watson winning Jeopardy! In 2011, that felt different, more about understanding language nuances, right?
Absolutely. Advanced NLP in action. And then AlphaGo in 2016 beating Lee Sedol at Go. That was mind-blowing because Go is considered way more complex, more intuitive than chess.
Right, the possibilities are astronomical.
Exactly. And now, since around 2020, we've got OpenAI's GPT-3 and models like it. These large language models have just fundamentally changed the game for natural language understanding and generation. It's what powers a lot of the AI chat stuff we see now.
So what fueled this recent explosion?
It's really a convergence of things. Just way more computing power, access to absolutely massive data sets to train on, and much more sophisticated algorithms, especially deep learning. Plus, crucially, AI development got more accessible. Open source tools like TensorFlow and PyTorch, specialized chips like GPUs, suddenly more people could build powerful AI.
So it moved out of just the labs.
Totally. Now it's baked into everything. Siri, Alexa, Netflix recommendations, Amazon suggestions, but also critical stuff like self-driving car tech, medical image analysis, financial modeling is really embedded now.
It's amazing tracing that path. Okay, let's dig into the mechanics more. How do these machines actually learn or see or get us, starting with machine learning?
Right, machine learning, ML. So fundamentally, it's about letting systems learn from experience, from data, without someone explicitly coding every single rule. Think about traditional programming. You write exact instructions. With ML, you give the algorithm lots of examples, and it figures out the patterns and rules to make future predictions or decisions. It's learning by example, basically.
Okay, and you mentioned different ways they learn. Supervised.
Yeah, two main types. Supervised learning is where you train the model on labeled data. Each piece of input data comes with the right answer or output label. Like teaching spam filters, you show it millions of emails already marked spam or not spam. It learns the characteristics of each.
So it learns from known examples. What else uses that?
Lots. Sentiment analysis, figuring out if a review is positive or negative based on labeled examples. Credit scoring, predicting risk based on past loan data. Fraud detection, identifying weird transactions based on patterns learned from known fraud cases. Even medical diagnosis, like AI spotting diabetic retinopathy signs from images labeled by doctors. Predictive maintenance, customer churn. Tons of stuff.
Got it. And the other type, unsupervised.
Right, unsupervised learning. Here, you give the model unlabeled data. There's no answer key. The system's job is to find hidden patterns or structures all by itself. Imagine giving it a huge list of customer purchases and asking it to find natural groupings or segments of customers.
So finding patterns we might not even know exist.
Exactly. Customer segmentation is a classic example. Amazon or Zara might use it to group shoppers based on buying habits. Market basket analysis in supermarkets, finding items often bought together, like, bread and butter. Anomaly detection for finding unusual, potentially fraudulent financial transactions. It's about discovering the inherent structure in the data.
That makes sense. So once you've trained these models, how do you know if they're any good? How do you grade their homework?
Good question. Yeah, evaluation is critical. We use different metrics depending on the task. For classification, like spam detection, we look at things like precision. How many of the emails we called spam were actually spam? And recall, did we catch most of the actual spam? The F1 score combines those. For predicting numbers, like house prices, we might use mean squared error. And really important are techniques like cross-validation. You don't just test on one set of data, you split your data up, train and test multiple times to make sure the model performs consistently and isn't just lucky on one particular test set. It's about building confidence it'll work in the real world.
Right, rigor matters. Okay, let's move into deep learning and neural networks. This feels like where a lot of the really cutting-edge stuff is happening, right? Those powerful language models.
Definitely. Deep learning is a subfield of ML that specifically uses these deep neural networks with many layers. And yes, they're loosely inspired by the brain structure. You have an input layer, then multiple hidden layers doing the complex processing, and an output layer. Each layer has interconnected neurons with weights and biases, processing info via activation functions. It sounds complex, and it is,
Mm.
but that depth allows them to learn really intricate patterns.
And how do they learn? You mentioned backpropagation.
Yeah, backpropagation is the core learning mechanism. Essentially, when the network makes a mistake, the error is calculated at the output. Backpropagation sends that error signal backward through the network. As it goes back, it tells each connection how much it contributed to the error, and the network adjusts its internal weights and biases accordingly to try and do better next time. It's guided by optimization algorithms like gradient descent, constantly tweaking itself to minimize errors. It's iterative learning from mistakes.
Okay, it's like refining its understanding over time. Are there different kinds of these networks?
Oh yes, several key types tailored for different data. Recurrent neural networks, RNNs, are built for sequential data where order matters, like language or time series. They have a kind of memory loop, allowing them to consider past information. Perfect for language translation where context is key, or voice assistants understanding commands, or even financial forecasting.
Makes sense for sequences. What about images?
For visual stuff images, video convolutional neural networks, CNNs, are the stars. They use special layers, convolutional and pooling layers that are really good at automatically finding spatial hierarchies of features in images. They learn to detect edges, then textures, then parts of objects, then whole objects. They power facial recognition, medical image analysis, finding tumors in scans, say, and are absolutely vital for autonomous cars to see the road, pedestrians, signs.
Okay, RNNs for sequences, CNNs for images. Anything else major?
Well, things get even more advanced. Generative adversarial networks, GNNs, are fascinating. You have two networks competing. A generator creates fake data, like images, and a discriminator tries to spot the fakes. This competition forces the generator to get incredibly good at creating realistic synthetic data. People use GANs to generate photorealistic faces, create art, design molecules for drugs, make 3D models, really cool stuff.
Wow, like an AI art forger learning from an AI detective.
Kind of. And then there are transformers. These have absolutely revolutionized natural language processing, NLP, recently. Their key innovation is the self-attention mechanism. It lets the model weigh the importance of different words in a sentence, no matter how far apart they are when processing any given word. It gets the whole context much better than older models like RNNs. That's the tech behind models like Google's BERT and OpenAI's GPT series. It's why they're so good at translation, summarizing text, writing coherent paragraphs, powering sophisticated chatbots.
That self-attention sounds like a game changer for understanding language properly. So speaking of NLP, let's focus there for a moment. Making machines understand us. How does that work under the hood?
Right. NLP sits at that crossroads of AI, computer science, and linguistics. The goal is enabling machines to understand, interpret, and generate human language effectively. It involves understanding syntax, the grammar rules, semantics, the meaning of words and sentences, and pragmatics, the context, the social use, the implied meaning. That last one's often the hardest.
Yeah, sarcasm must be tricky for AI.
Oh, definitely. So a lot of NLP starts with text pre-processing, cleaning up the text data. That means things like tokenization, breaking text into words or pieces, stemming or lemmatization, getting words down to their root form, like running becomes run, removing stop words, common words like the, a, that don't add much unique meaning. This gets the text ready for analysis. And as we've said, this powers voice assistants, chatbots, translation tools, anything involving language interaction.
Okay, cool. And the last big piece you mentioned was computer vision, AI learning to see. How does that happen?
Computer vision aims to train computers to interpret and understand information from images or videos, just like human vision does. It uses cameras, data, and algorithms. Like NLP, image data often needs pre-processing first, maybe converting to grayscale, adjusting contrast with histogram equalization, normalizing pixel values, using edge detection algorithms to find boundaries.
Preparing the image for the AI's eyes.
Pretty much. A huge area here is object detection. Not just saying, there's a cat in this image, but drawing a box around the cat and saying cat, and maybe another box around the dog, saying dog. Techniques like RCNNs, SSD, and especially YOLO, which stands for You Only Look Once, and is known for being super fast, are key here. Essential for real-time things like security cameras spotting intruders or self-driving cars, identifying pedestrians, bikes, other vehicles instantly.
So finding what is where.
Exactly. There's also image classification, which is assigning a single label to the whole image. This is a picture of a beach. And image segmentation, which goes even further, partitioning an image into pixel-level regions belonging to different object classes. Think highlighting the exact shape of a tumor in a medical scan, or distinguishing the road from the sidewalk for a self-driving car.
It's incredible how these pieces fit together, but all this power naturally brings up big questions, doesn't it? What about the human side, the ethics?
Absolutely crucial. As AI gets woven deeper into society, the ethical considerations become paramount. We're grappling with fundamental questions, like how much autonomy should machines have? Who's responsible when an AI makes a mistake, especially a harmful one? Think about a self-driving car accident, who's liable? And what about the impact on jobs as automation increases? These aren't easy questions.
No, definitely not. And bias seems like a huge one, too.
A massive one. Bias and fairness. Because AI learns from data. If that data reflects existing societal biases, the AI can learn and even amplify them. Herman's work points to facial recognition as a key example. Some systems have shown significantly lower accuracy for certain racial groups, which can lead to real-world harm, like false arrests or unfair access denial. It really highlights the need for diverse, representative training data. We also need transparency in how these systems work, and tools like IBM's Fairness 360 Kit to help developers actively find and reduce bias in their models.
So it's not just the tech, it's the data and the design. What about privacy? AI seems hungry for data.
Extremely data hungry, often. And that raises huge privacy concerns. These systems can collect vast amounts of personal, sometimes very sensitive information. How is that data collected, stored securely, used? Could it be misused? We need strong data protection. Things like anonymizing data where possible, encrypting storage, and clear rules about consent and usage, like Europe's GDPR tries to enforce.
It feels like we need rules, some kind of governance.
Definitely. Regulation and governance is a hot topic globally. But approaches vary. The EU is often seen as more proactive with comprehensive rules like GDPR and the proposed AI Act. The U.S. tends to be more sector-specific. There's a growing push for international cooperation and common standards through groups like the Global Partnership on AI to try and ensure responsible development everywhere. But it's complex, finding the right balance between innovation and safety.
So many challenges. But looking forward, where is AI heading? What's exciting on the horizon?
Oh, the future is incredibly dynamic. Several emerging areas could be transformative. Quantum computing is one. While still early days, quantum computers promise calculation power far beyond current machines. If harnessed, they could revolutionize AI by solving problems currently intractable. Think complex drug discovery simulations, breaking modern encryption, or optimizing massive systems.
Wow, okay.
What else? Edge AI. This is about moving the AI processing off the cloud and onto the local device itself, your phone, your car, your smart speaker, a medical sensor. This drastically reduces latency, the delay. Crucial for things needing instant response, like autonomous driving or real-time health monitoring. It also boosts privacy because your personal data doesn't necessarily have to be sent to a central server. It stays on the edge.
Faster, more private AI. Makes sense.
Then there's explainable AI. As AI models get more complex, especially deep learning ones, they can become black boxes. We know they work, but we don't always know why they reach a specific decision. XAI develops techniques to make AI outputs interpretable, understandable to humans. This builds trust, helps us debug, find hidden biases, and it's essential in high-stakes areas like medicine or finance, where you need to understand the reasoning.
Opening up the black box.
Exactly. And finally, a really positive trend is AI for social good. A growing movement to use AI specifically to tackle major global challenges. Things like using AI for environmental monitoring, predicting climate change impacts like Microsoft's AI for Earth initiative, using it to improve public health responses, track diseases, or even optimize resource distribution and disaster management. It's about harnessing this power ethically for humanity's benefit.
That's a much more hopeful angle. And, for anyone listening who's maybe feeling inspired by all this, thinking about getting involved, it sounds like Python is the place to start.
Yeah, absolutely. If you're curious about development, Python is definitely the go-to language in the AI world right now. It has an amazing ecosystem of libraries specifically for AI and machine learning, TensorFlow, PyTorch, Scikit-learn, Keras. They make it much easier to start building things. Setting up a basic development environment isn't too hard, and there's a huge, helpful online community. It's a great time to explore.
So quite a journey we've taken today. We've gone from defining AI and looking at its surprisingly long history through how things like machine learning, computer vision, and NLP actually work, all the way to these critical ethical debates and glimpse into the future. We covered a lot of ground.
We really did. And I think the key takeaway is that AI isn't just some academic concept anymore. It's deeply woven into our lives, and it's changing and growing incredibly fast. The potential is enormous.
Absolutely, but it also comes with this huge responsibility, doesn't it? Balancing that potential with careful ethical development and use.
Precisely. Which maybe leaves us, and you listening, with a final thought to chew on. As we move into this future where human intelligence and artificial intelligence are increasingly intertwined, constantly pushing boundaries, how will you play a part in making sure this incredibly powerful technology is used responsibly, ethically, and ultimately for the benefit of everyone?